Hi, good afternoon to all. Thank you for taking the time to dial in today. Shilling and I are recent graduates from NUS ISS Masters in Technology, Intelligent Systems, otherwise known as AI. We canvassed for our final capstone project, mid 2021, and were very fortunate to be given an opportunity by RapidScan to help pilot a solution to detect biodiversity threats. In this presentation, we'll be showcasing an innovative method leveraging on TensorFlow Object Detection API to process and detect hiking shoes in baggage. The agenda for today is business problem, technical challenges, overall technical approach, experimentation, results, and conclusion. Let's take a look at the business problem. Airports globally have implemented advanced security screening to maximize threat detection for prohibited items in baggage stemming from both security and custom related concerns. Baggage scanner machines are typically powered by X rays. They deliver an integrated and automated systems for object detection. The newer technology uses 3D X ray CT imaging systems, computed tomography, that's actually traditionally built for medical diagnosis. They use this for check pages and they rotate around your baggage to generate a density map of 2D slices images. Recent emphasis on biodiversity threats call for detecting objects that potentially carry soil contaminants and even diseases. So RapidScan, this is our sponsor, who is a market leader in this field, embarked on a groundbreaking trial with Australia using the 3D X-ray technology in a biosecurity environment. This was done with this RTT 110, which has the ability to use auto detection algorithms for risk screening to create an extensive biosecurity risk image library. Lately, Australia has identified certain shoes here as potentially carrying contaminants and is working with RapidScan for proof of concept to maximize such threat detection brought into the country. So this is where we are, and this is what we're actually working on. So what are the technical challenges that we have? Pre-COVID, let me look at pre-COVID. So pre-COVID, I'll be very cool, I'll pack my things. This is typically my luggage. My shoes will be in one corner, my slippers in another. You have the camera, and then I have my toiletries bag. Technically, my luggage would be, well segmented. Every compartment will have something like that. And this is my very, very neat luggage bag. This is my way. Unfortunately, post-COVID, when I packed my bag in a very rushed manner, not knowing what to put as well, you'll notice that my bag is full of a lot of cluttered materials and items inside here. So you can see, okay, I've put two pairs of shoes here, but the shoes are overlapping each other, maybe blocking each other a little. Okay, maybe the shoes, some of them you see the side views out there, you see the soles. Everything is actually cluttered and overlapped as well. So this is basically the reality we are dealing with in the typical luggage. As you can see, right, security inspection often deals with a baggage where objects are randomly stacked and heavily overlap each other. So these are a lot of challenges that we see here. In the scanned images, right, what you want to actually look for, the objects of interest, may be mixed with arbitrary and meaningless clutters and cannot be even detected. This results in also occlusion, partial views, and poor performance of the models created as well. And even, where you place it and how you place it, like the shoes, is it a side view, etc., could also be an issue. If you look at the training set, although we do see limited X-ray baggage images available online, the sensitive nature of the X-ray baggage images hinders the availability of large data sets. For this project, they worked with RapidScan on 251 3D images of 10 types of shoes, augmented and annotated. It is an accurate data set, but still, it is very small. And here, right, you look at the viewpoints issues. We have a lot of intra-class class variations, which are a very big challenge for us. So if you imagine, right, the different designs we have for sports shoes varies in shape, structure, material, with possibly even, very few shared features as well. This could lead to poor generalization when deployed in the real world. It means that you need to have many different types of shoes, many different types of sports shoes to make it work better as well. So this is an intra-class issue problem that we have. And if you look at what is class imbalance, so class imbalance, right? Let's look at US. About 6,000 firearms were seized at airport checkpoints in 2021 by TSA US. So it converts to one firearm, right, detected for 100,000 of passengers going through. It's a 0.001%. Okay, this is a kind of unbalanced kind of data set that we're looking at. And it renders modeling of appropriate unbiased techniques very, very difficult. If you look at the last part, this is also the biggest one that we have here, the belt speed. If you put a bag on and it goes through checking, the typical speed of the belt is 0.35 to 0.5 meters per second. It means that for rapid scan, the 110 that you see there, it can process 1,800 bags per hour. Every bag, 2 seconds. This is the amount of time we have to infer. We have to send the data, infer it, come back and say, okay, this is okay and this is not okay. So imagine for all of these, right? A lot of academic studies have proposed very high performance models, which simply cannot be implemented in real time with this kind of requirements. So if you look at it, the accuracy has to be balanced with all these technical challenges here, particularly the inference speed. The current trial they actually have for rapid scan is based on a 3D technology where objects of interest such as meat is actually detected using a segmented approach. And then they have actually achieved quite a big success. A smaller percentage of bags are open for inspection, but the high percentage of inspected bags contain actionable biosecurity risk material. 3D technology has actually resulted in more than twice as many seizures of meat products compared to existing 2D X-ray technology. So, when you try to bring a meat into like Australia, like, this lady with a half-eaten sandwich and things like that, these are the issues that you face because they have very high accuracy for this. However, this has actually proven to be very ineffective against shoes because you'll see that there are multiple blocks being created, like, at the top half of the shoes, at the soles, the shoelace, and, any metal fasteners. And it has also compromised the inference speed. So this method cannot be used for the shoe detection as well. So we started to look at some of the related work that people had done on the security screening. Typically, it can be grouped into classic image analysis, machine learning, and deep learning. Here we see deep learning basically split into 2D and 3D. In the 2D here, right, it's actually with a CNN. They're actually connected at the last layer and mostly using a bounding box with a SSD and YOLO. Or you can also use a two-stage multiple region proposals with RCNN, RCNN, and parser CNN, etc. So this is a 2D approach commonly used to detect objects. Here, on the 3D basis, the data would be a 3D data train of RGBD, point cloud, or like the tomography, which we have, computed tomography, CT, 3D MRI. And then you use models like BoxNet, PointNet, VoxelNet, and SliceNet to work out as well. So if you look at SliceNet, right, it's actually similar to what we initially considered. So when they slice it and then, they fuse it basically to get the image and get the results they want. But the point is it took up about 7 seconds to get one inference per bag. This is out of range. And then we look at, what are the data sets and everything that we have on the security here. So there are a number of data sets that are available. The most popular and the biggest one is 6-ray. It's actually done by the Chinese. Every time you go through the Chinese transportation, you will have to scan your bags. And they've collected 1 million bags with, 6 categories of knives, everything that you cannot bring onto the train, etc. Here, this is one of the more common ones that's being developed recently that's actually used for consumer. And there are others as well that's actually being built up as well. And if you look at this column here, security inspection, what these people, when they create the data set, some of them have actually managed to use different ways of pre-processing the data set so as to reduce some of the issues that we face. For example, occlusion. So here, right, they will actually use a de-occlusion attention module, whereby they will create a model and plug it into a 3D model so that it will be basically the objects will be less occluded. And then if you look at class imbalance hierarchical refinement, this will also be something that is created to help ensure that the class balance issue is minimized. So here, this block basically has the data processing to help into these models, the deep learning models. We have actually evaluated 3 technical approaches and trained our data sets, including 2D, 3D, and the projection-based kind of a method. In the 3D method, right, we use complex YOLO to train and validate data set. Efficiency and memory optimization were also done to improve speed for faster inferencing. For projection, a slicing-based object detection method was developed. Inter-slice prediction can then be done with a time series model to improve detection in cluttered bags and faster inferencing. However, these 2 methods still had issues of slower upload, inferencing speed, and high computational costs. Insignificant performance advantages were also observed. So, with all these disadvantages, we decided to stick to the 2D. We finally decided on the TensorFlow object detection API, but we use an innovative method in the pre and post-processing method to achieve what we actually want. My teammate Shilling will continue with the multi-slice twist we have added in the technical experimentation. So over to Shilling, please.
Yeah, thanks, Maureen, for the introduction of the project. So before I go into the details of the strategy that we are using, right? So here's an overview of the system architecture. As you can see, inferencing is actually done in the cloud through AWS. So Repliscan has actually their own proprietary scanning system where the package will be fed into their scanner machine and then through their system. The 3D images are actually being converted to a 3D NumPy array. Then the NumPy array will then be processed and then fed into the S3 bucket, which will trigger the Lambda function to actually perform the inferencing through the detection model that is stored in the Elastic Container Service. I'll talk a bit more about the details of the pre-processing steps in the later slides. Next, please. Yeah, so here is the overview of the technical strategy that Maureen mentioned. So as earlier highlighted by Maureen on the technical challenges, especially on the occlusion and the inferencing speed. So clearly from an implementation point of view, we have to go with 2D instead of 3D, just for the fact that 3D inferencing will be too slow. And then it will be too slow to be practical. So from the past work that we studied based on 3D, right, although the detection can be accurate, but the inferencing speed is just in order of seconds. It's just too slow for our use case. So we need the inference speed in the order of milliseconds, which we'll be having since we are having large volumes of baggages. Then the next thing we did was that we actually applied thresholding to the NumPy array to remove non-hard objects. Visually, what it means is that imagine a 3D image that is being converted to a 3D NumPy array with only one channel or black and white. So how are the values in the NumPy array represented with respect to the objects? So objects like clothes, paper, or very thin objects will have a very small value compared to those hard objects like the sole or the boots, the metal objects, right? So what we can do is that we can actually set a threshold or range where only the hard objects are retained. So in this way, what we meant by thresholding. So it's quite a common technique used in image processing. So this technique is also able to help us to reduce those clutters. Especially we remove all those clothes and stuff that are non-hard objects. Okay, next is the key point of our project is that what we do is that we actually do a multi-slice. So what we did is that we actually slice the image at different depth and do a projection to create 2D images. And then after that, we concat them into a single 2D images. On the later slide, I will have a more detailed explanation of this technique. Next, please. Yeah. So on the left image, right, what you can see is that what I meant on the multi-slice method is that, as you can see, what we actually do is that we actually slice the image by half. And then first we retain the upper half, and then after that we retain the lower half and followed by the middle portion. Then after that, what we do is that we actually apply a projection from the top view by simply retaining the max value of the from the top plane. And then the rest of the values will be 0. So the bottom image at the middle of the slide is an example of the projection. And then what we do is that we actually concatenate all the different slides into a single image as shown on the right. So the right image is a very good example of what our strategy is about and also explains the benefit of our strategy. As you can see on the right image, right, there are actually four different slices that you can see. The top left is actually the original projection. That means there's no slicing at all. And then the top right is actually the lower half. And then the bottom left is actually the upper half. And then the bottom right is actually the middle portion. So what you can see is that actually the original image, right, is showing that there are actually two pairs of shoes stacked on top of each other. If without this multi-slice method, right, what will happen is that the bottom part of the shoe, which is the golf shoe, right, will be blocked by the upper shoe. So this is sort of like the occlusion, the occlusion that we are facing. So by doing this slicing, right, what we do is that we are able to uncover or unblock those objects that are actually hidden below. So that's our gist of our technique lah. Yeah. Next slide, please. Yeah. So here is basically just a general view of the how our flow, our project is in terms of the data preparation and then the model training and then the testing as well. The key takeaway here is that for this project, right, we actually leverage on what is already available out there from all the big tech companies like Google or Facebook, where they already have a very comprehensive list of pre-trained models that we can use. Because no point reinventing the wheel to come up with our own model architecture, given that for as individuals, we have very limited resources in terms of a GPU usage. And then compared to those big tech companies where they have practically unlimited GPU resources to train the models. So it makes sense to actually use a pre-trained model itself, building our own. So in this case, right, you can see on the left, right, based on the processing step. So what we did, we just, it's quite a standard data processing step where we split the data to train and train and test, and then after that we do a pre-processing step, which I will explain on the later slides. And then on annotation part, right, we actually use the label image tool that is available free on GitHub. So this is a very so-called user-friendly annotation tool that which also happens to be compatible to the TensorFlow objection detection API. So this is the annotation tool that we use. Okay, then on the training part, right, we'll be using Colab as our training platform. And then the metrics that we're going to use, right, the performance metrics we're going to use will be the same metrics that we use to evaluate the full core data set. Okay, the reason why we are using these metrics is because the pre-trained model that we are using is also trained using this COCO data set. And also because this evaluation metrics, right, is already available at the GitHub. So we just port over, since the pre-trained model is using the same data set, and then the evaluation metrics is using this average of precision. So we adopt the same performance metrics as what is being used by this for pre-trained model. Beside this average precision, we also look at the classification loss and also the localization loss. Yep. Yeah. So next slide, please. Okay, here is just an overview of the data set and also the classes and all the shields are what are being looked like. So in all, we have 10 classes based on the data set that was provided by RapidScan. Just take note that you can see that for every data, right, the NumPy array, the size is actually is a standard size of 1024 by 640 by 860. So regardless of the size of the luggage, whether it's big or small, or even the orientation of the luggage, right, all the 3D images will have this standard size of 1024 by 640 and 864. Next slide, please. Okay, here so basically, here is just talking of is the description of the data processing step. So as you can see, right, on the left, the first step is what we do is that we actually crop the blank space. Remember that the standard NumPy array the 3D NumPy array we have is 1024 by 640 by 864. But then that's the standard size because the luggage will so depending on how big the luggage, there will be a lot of blank spaces outside of the luggage space. So what we did is we actually crop away all those blank space. So that's the first thing that we did. And then after that, on the second point, right, what we do is that we actually, based on the shape of the remaining crop image, right, we actually do a realignment such that the length of the luggage will always be on the horizontal plane, and then the height is always on the vertical plane. So that this give us a consistency where you don't have luggage where they are standing or they are tilted or they are on a different orientation. So we do this realignment to make sure that all the luggage are always facing flat, just like what is being shown on the point to the image at the top. Then after that, of course, then we do our slicing, then followed by our projection, and then after that, we do a concatenation. Next slide, please. Okay, so basically, like I mentioned earlier, right? So the annotation tool that we use is label ink. So this is just an illustration to show how we do the annotation after we do the concatenation into a single image. Next slide, please. Okay, so this is just a overview of the training. So the training is done with batch size 16, as mentioned earlier. So okay, so the center image, right? The center image where you have the four luggages. So this is actually showing an example of the inference. So after inferencing, as you can see, right, all the four different baggages will have their own object detected. So what we do is that we actually do a post process to actually combine every detection back into original image that is being shown on the right side. Okay, this example also show the clever part of the multi-slice technique, which whereby you actually don't have to detect the objects in all different all four different slices. So just imagine, take for example for this particular example, right? As you can see, the bottom left of the inferencing result, right, is actually the golf shoe, but it's only appeared on the bottom left. So the good part about this technique is that even though originally this golf shoe was actually being blocked by the working shoe on top, right? After slicing, we are actually able to sort of like unblock this golf shoe. And then what happens is that because of our clever post processing, you only need to detect one out of the four. So in order to detect what you intended to use, so that's the good thing about it. You don't have to detect all four at all different four viewpoints, but you need to detect one out of four. Yep. Next slide, please. Okay, so here is basically just the training results that we have. So as mentioned earlier, we use the mean average precision that is the same performance metrics that is done on the Coco dataset, which is also used to pre-train the models. So basically we have evaluated four models, the evaluation depth, the SSD mobile net version 1 and version 2, as well as the SSD ResNet 50. So all in all, you can see that the overall the best performance will be the mobile net V1 version 1 with a mean average precision score of 60.4. Just for comparison context, right? The Coco data set, the evaluation that's done on the pre-trained model, right? The score is actually only about 29.1. So the scores of 60.4 is actually a very good result. Yeah. Next slide, please. So with that, right, I sort of like conclude the overall presentation. So the key takeaway from our project is that we are able to actually overcome the occlusion issues and also as well as the influences by introducing this 2D multi-slice technique that we introduced. And then for future development, of course, we are looking at because of the limited data set that was provided to us. Right? So for future development, we are also looking at how we can acquire more data sets to make the model more robust, as well as also looking at now we are only slicing it three parts. So we are also maybe perhaps want to explore slicing more of them, and also looking at other models because I think right now there's a lot of attention on attention models that is being used on classification as well. So this is also one area that we want to look at. Yeah, yeah. So that's concludes our presentation. Yeah.
Okay, thanks, Maureen and Chilling for the insightful sharing of their projects. Hi, I'm Jen Hong. Apology for the technical errors we had in the beginning of this session. Before we start the Q&A sessions, we would like you to do a survey to help us understand how can we help you in deep tech area. You can simply scan the QR code and you will be directed to a Google form. no personal information is collected in this process. So back to the Q&A. For Maureen and Chilling, I think it is good that you have proposed a system that runs more efficiently to detect a biotrack in luggage. Now, out of curiosity, according to your system architecture, the model is going to park in AWS. Do you have any idea how much time is your system going to take to completely analyze a luggage?
Let me take this question. So as you all understand, right, we only have a maximum of 2 seconds for each bag to, to actually have a result, and then it will go out. So typically, right, with what we have actually set up, we are expecting is going to be definitely less than 1 second. It will be in the milliseconds. Upload and download, would be in it's a very small image because we're actually concatenating all of it together. And then the inference will be like 0.48 seconds. So all in all, less than 1 second, you get the result that you want.
Okay, that's considered fast. I think that works for the purpose. And the next question I would like to know, in your solution, you have sliced the 3D arrays in 4 separate ways. Have you considered slicing the arrays in a larger number of ways, 6 or 8? Are there any specific reasons that you didn't choose to slice the 3D arrays 4 ways?
Yeah. Thanks, Jenwan, for the question. So let me take this question. So in terms of the slice, right, why we do this, right? Actually, there are two main considerations. So firstly, we consider the typical shoe as compared to a typical luggage size. So slicing it the way that we did, right, sort of makes sense because it sort of like retains a reasonable size of the shoe. Because we don't want to slice too many times where you no longer the shoe no longer look like a shoe. So this way, this is one of the consideration in terms of the shoe size with respect to the luggage size. So that's consideration number one. The second consideration is actually got to do with the input size to the inferencing model, because remember we are using the pre-trained model, right? So the input shape to the pre-trained model is a square image. So you have a choice of actually either 320 by 320 or 640 by 640 and so on and so forth. 1024 and 1024. So it's actually a square image. So remember when we slice it and when we concatenate 4 images, right? So in order to make a square, so it's better to have a 2 by 2 like 4. That means we have 4, yeah, you concatenate 2 by 2 to make a square, or 9, 3 by 3, 9, uh, uh, or 16 or 4 by 4. So if you think of this way, right? So if you were to go by 9 slice or 16 slice, right, the slice will be too thin. So that's why if you consider the input shape, which is a square, right? We stick to 2 by 2. So of course you can also choose to go 6 slice or 8 slice. But then if you go 6 slice or 8 slice, right, when you concatenate, it will not be a perfect square, it will be a rectangle shape. So of course you can do a reshape and stuff like that, but then you also like distort the image. So we want to avoid this distortion of the shoe. So we stick to 4, which is 2 by 2. So that's the two consideration. Yeah.
Question.
Yeah, just a very quick add on also. We also did consider like the size of a typical shoes, and then when we actually decide on how much to cut it, and we find that cutting in the manner that we have decided that Chilling has also mentioned will basically cover and uncover what we think are the occluded items of shoes as well. Yeah.
Okay, here is another one question from the ground. If the luggage is odd shape, how the slicing is going to work?
Okay, because when as I mentioned at the earlier slides, so the first thing that what we do is that we actually crop away all the blank spaces. So let's say for example the I mean it doesn't matter whether how the shape of the luggage is. For sure, it will have a x as a length, a width, and a height, right? So what we do is that the first thing we do is that we crop away all the black spaces. So we just keep the luggage, and then after that, what we do is that we based on the length, the height, and the width of the luggage, right, we actually reorientate so that the luggage will always be the same orientation in a way. So that's how we approach it. So once we've done that, right, then we do the slicing. So to answer the question, right, is actually no matter what kind of shape of the luggage, right, we will still go through this process. So ultimately, the long side of the luggage will be on the horizontal side, and then the height will always be facing vertical, and then we just slice it this way. Yeah.
Okay. I think due to time constraint, we have the last question for you. Other than bio thread, how about conventional thread like guns and bullets?
Okay, guns and bullets, right? Basically, there are many different ways that they have actually detected. So, for example, X-ray, right? They're able to rapid scan. They have actually used a color coding. They're able to detect the material, and of course, now there are like plastic ones as well. But it is basically a model that's already trained and very well established, I would say, for the of such objects. It's just that the newer objects like shoes are not there. So like in terms of security, knives, all this, no issue. They are already in place. So you'll see that they use those segmented approach as well. Yeah.
Okay. I think that's all for this for their sharing. Thank you so much for your sharing. Next, I would like to invite Dr. Barry Shepherd, who about ISS Master of Technology and Graduate Certificates in Intelligent Systems.
Hey, good afternoon, everyone. I'm Barry Shepherd, as Jen Hong just mentioned. I'm the chief of our Intelligent Systems program here at the Institute of Systems Science. I'd like to take just a few brief moments to talk about our Master of Technology program and our graduate certificates in Intelligent Systems. So I'm going to be very brief. I'll start off with just a little overview about what intelligent systems are, and then drill down a bit into the topics that we teach and the structure of the master's course. And then, of course, lastly, how and when to apply. So what are the key ingredients of an intelligent system? So, of course, we've all heard the terms artificial intelligence, machine learning, deep learning, and these are going to form the core tools from which we build our intelligent systems. But to build an intelligent system, we, of course, need some input. So that's where sensing technology and sensing data comes in. It's very important, forming the inputs, whether it's from cameras in the streets or wearables on our wrist or any of the other sensors that are going to be spread around the city. And of course, once we've input the data into the decision making, we then need to take action and turn that into some concrete action. So it could be moving a robot, or it could be controlling an autonomous vehicle or a drone, or even making a buy-sell decision and a sort of a real-time trading system. And of course, let's not forget the feedback loop where we try and use machine learning to learn how to improve our decision-making based on the actions we take. So some examples of intelligent systems. Of course, we've all again heard of the term Industry 4.0, the application of AI within industry. So the photo there is showing a robot and a man in cooperation. It wasn't that many years ago where robots had to be kept well away from people in factories because of the safety reason. But now with better AI control and better sensing, we can have them cooperating together. But of course, Industry 4.0 is not just robots in factories. It's the whole process going from intelligent supply chain through to flexible manufacturing and better distribution and logistics. Smart city is another big application I'm sure you've heard of, smart city and the Internet of Things. But again, the Internet of Things and smart city is not just having intelligent waste bins or intelligent refrigerators that know when to order fresh food. It's optimizing the whole workings of our city, whether it's transportation optimization or power grid optimization or waste disposal optimization. Vision systems, as you've just heard this afternoon, we're seeing an awful lot of vision system applications. Our students are doing a lot of projects involving vision system developments. So it could be surveillance or monitoring in the street, or it could be monitoring people on building sites, I know building site safety is something that's been cropping up in the newspapers these last few weeks. Monitoring how people are relative to cranes and other equipment in the building site to make certain that they're kept safe. Or, of course, it could be facial recognition or just inspection of images, for example, inspection of medical images of chest x-rays and so forth. And last but not least, let's talk about the many business applications of AI and intelligent systems. So it could be enhanced robotic process automation, software robots that are helping to automate middle management tasks, enhanced with AI to allow them to do more complex automation tasks. Or it could be building better customer service agents or bots, like better chat bots, intelligent assistants or recommendation engines, and so forth. So why would you wish to take the MTech in intelligent systems? Of course, in my view, it's going to lead you into a career where you get the chance to build lots of exciting and challenging systems. And there's a long list of job scopes here on the slide, but now we're finding AI and intelligent systems are being adopted across nearly all industry domains. And this program would be suitable for you whether you want to change your career and suddenly go over and become an AI expert, or whether you want to use the additional skills to enhance your existing career. So how is the course itself structured? So as you'll see here, each vertical column is what we call a graduate certificate. So those graduate certificates are designed to be self-contained and configured towards essential skills for a particular job role. So the yellow ones on the left are the fundamental certificates that you must take. And then the pink ones on the right, you take 2 of these 4. And these are specialist certificates that are configured towards specific application domains, such as intelligent robotic systems. So each column, each grad cert, comprises usually about 3 or 4 individual course components. And those individual course components last between 3 and 5 days of class. So typically to take a grad cert, you're taking about 12 or 14 days of class. So how does it all work over the course of your studies? There are a couple of different ways of taking our master's program. The structured route is where you apply, qualify, and register upfront. So you're registering as an NUS master's student upfront. So you can either do this as a part-time student studying on Saturdays over a course of 2 years, or you can do it as a full-time student studying during the week over a 12-month period. All study days are full-day studies running from 9 o'clock in the morning till 5 in the afternoon. So as a part-time student, which is the chart on the left, you would do 1 grad cert every 6 months, every semester. So you would take your 2 fundamental grad certs in year 1, and then in year 2, you would do your 2 specialist grad certs. And in parallel in year 2, you would be taking a capstone project, which is a team-based project where you work with your classmates on a real industrial problem. If you're doing the full-time program, then the capstone project takes the form of a internship project where you are seconded within an industry sector or a company within Singapore, again to work with some of your fellow classmates on a real industrial project. There is another way of taking the master's program, and before I get onto that, there are exams, of course. At the end of each grad cert, you take an exam. So since you're taking 4 grad certs for your master's program, you'd be doing 4 exams, and they are occurring at the end of each semester. So the third way of taking the master's program is through the flexible or stackable route. And with this flexible route, no need to register with NUS when you start. You simply select the individual course components from our short course executive education calendar, which is online on our website. So you have 5 years to complete the 4 grad certs. So you'd be taking about 12 4 or 5 day courses within a period of 5 years. And then providing you pass the grad certs with an overall cap of 3.0 or more, then you can then register with NUS and go on to take the capstone project, which you're allowed another 2 years for. So if your family life is and work life is very busy, then maybe the flexible route would be more appropriate for you. What are the admission requirements? It's a master's program, so clearly you must have an undergraduate bachelor's degree from a recognized university. Typically, this is in engineering or science, but it does not have to be. We often have very successful MTech intelligent systems graduates, perhaps, that come from more of a management background. The grade point average for your first degree must be greater or equal to B- or 60%. The second main requirement we have is that ideally you have some work or project experience. We say ideally 2 years or more, but we're very flexible on this in the Intelligent Systems program. We'll look at what your work or your projects involve. And clearly we're looking to see whether they involve topics that are related to intelligent systems. The third bullet here, computer programming ability. This is a must-have. During the course of your studies, you're going to be building systems. The whole master's program is giving you the skills to build intelligent systems. So you're going to be coding and building software systems. So you need a good programming ability. And you'll find now that most AI systems currently are being built using Python. And that's the language we use for our workshops throughout the course. So we really recommend that you have some good Python experience. And then the last 2 bullet points here are, we have our own separate Institute of System Science entrance test. Not a big deal. It's just 60 minutes of multiple choice questions. There's a sample on our website. You must also pass a small interview, just 30 minutes. Last but not least, the important dates. If you're considering the part-time program that begins in January of next year, the admissions are still open. So please apply as soon as you can. For the full-time class beginning in August of next year, then the admissions will begin in October. And of course, if you want to take the stackable flexible route, then you can begin anytime. Just go and take a look at our short course calendar and select from there. If you want more details and looking at the fees and all of this, then you need to go to our website, and it's all covered there. So please go to the website and take a look. And it would be great if I can see you next year as a master's student here at ISS. So that's all I have time for, and thank you very much for listening.